discussed today: step response, impulse response, and complete response. You have been acquainted with these terms in the signals and systems. In the context of circuit theory, we shall illustrate this. Since you know the general principles, we shall illustrate this with the help of a few examples, a series of examples. First, we take the well known RC network, and we assume that V sub C 0 minus is equal to 0. That is, the capacitor is initially relaxed, and we connect an impulse voltage source delta t here, and we wish to find out the current I of t. As you know, the the only one mesh equation, delta t would be equal to R I of t plus 1 by C integral 0 minus to t I tau d tau. And the simplest way of doing this is to take the Laplace transform of both sides, and you get 1 equal to R capital I is the Laplace of small I, plus I by C s, and therefore capital I of s is equal to 1 divided by R plus 1 over S C. Is it okay? Or capital I is equal to S C divided by S C R plus 1, which I can write as, I always write the denominator as S plus something, coefficient of S is made unity, so we write S plus 1 over C R, and then we shall have S, and here we shall have 1 by R. Have I made a mistake? C and C cancels, okay, and this I can write as 1 over R S plus 1 over C R minus 1 over C R divided by S plus 1 over C R. I am just making some simple algebraic manipulation so that I can write this as 1 over R 1 minus 1 over C R 1 over S plus 1 by C R. Agreed? Now, the inversion of this is extremely simple. The inverse of 1 is delta t, and the inverse of 1 by S plus alpha is e to the minus alpha t times u of t. U of t of course has to be there, and therefore my I of t becomes equals to 1 by R delta t minus 1 over C R e to the minus t divided by C R, the whole thing has to be multiplied by u of t. This is what the current response is, and you notice that it consists of two terms. There is an impulse function. There is an impulse function in the term. If I plot this, then I shall have an impulse here, and an impulse is represented by an arrow with the value of with the strength of the impulse written by its side. The strength of the impulse is 1 by R, all right, and the second term the second term obviously is negative to start with. At t equal to 0, it is 1 by C R squared. This R also comes into picture, C R squared, and then it goes down exponentially. So this level is minus 1 by C R squared. This is the plot of I of t versus t. Okay. The question now is, the impulse is effective only at t equal to 0, because it exists at t equal to 0 only. T equal to 0 plus it is 0, t equal to 0 minus it is 0. It is exactly at t equal to 0. Okay. Now, the question, the next question that arises, suppose we wanted to find out this unit step response, then do we have to proceed ab initio, or does this does this give a clue to the solution? You see, unit step u of t by definition is 0 minus to t delta t dt. Okay, unit step is the integral of the unit impulse, and therefore, because it is a linear system, the unit step response, that is I u t, if I call this as I delta t, that is the current response due to a delta function excitation, then the unit step response excitation would be simply integral 0 minus to t I delta tau d tau. Okay. If the excitation is integrated, the response should also be integrated. This is the basic principle of a linear system, and therefore, what I can do is I can integrate this and get the unit step response. That is, if the excitation was a u of t r and c with v sub c 0 minus equal to 0, then the response, current response I u of t shall be equal to the integral of that, and I have carried out the integration. It turns out to be a very simple thing, 1 by r e to the minus t by r c multiplied by u of t. This is what it turns out to. Or else, if you do not like to integrate, well, this integration involves cancellation of terms and so on. Okay. You might like to do it directly, and directly means that capital I of s now shall be 1 by s, that is the Laplace of u of t, and divided by the impedance r plus 1 over s c, and therefore, this simply becomes c divided by s c r plus 1, which is equal to 1 over r 1 by s plus 1 over c r. So, this is no more complicated than finding the response to an impulse function, and all that you have to do now is to invert this, and obviously the inverse would be the same as this, 1 by r, then 1 by s plus c, 1 by c r is e to the minus t by r c times u of t. Okay. So, either way, whatever is convenient for you, it is either either you find the impulse response, then you integrate it to get the step response, or you proceed directly in the frequency domain, the Laplace transform domain.
But you will find the impulse response, and then you will be deviating from 0 minus to
0 minus to t.
0 minus to t.
That's right. Okay. On the other hand, if you know the step response, then you can find the impulse response by simply differentiating. If you know the step response, then you can find the ramp response. A ramp is a linearly rising function with an angle of 45 degree, which is exactly the integral of u of t, and therefore, if you know the step response, if you know I u of t, I r of t, that is the response to a unit ramp would be simply integral of I u of tau d tau. Okay. These are the 0 minus to t. These are the simplifying relationships that hold only for linear systems. If the system is nonlinear, such niceties are done away with. By definition, nonlinear is also a time consuming affair. Solving any nonlinear network is a time consuming affair. Our second example is to make a to bring variety into life. We now consider a step response excitation, that is, this switch is closed at t equal to 0, a current generator, and instead of a series circuit we take a parallel circuit. The same R and C elements are there, V sub C 0 minus equal to 0, and this voltage we treat as V. It is our intention to find V of t. Okay. That is a second type of response, and the and you see, I can either write the differential equation, solve it, or I can go directly into Laplace domain, because the initial condition is 0. I do not have to write the differential equation, but mind you, if the initial condition is not equal to 0, then you must write the differential equation and take Laplace transform term by term, because initial condition term imposes a driving function, the equivalent of a driving function. Okay. So, here to bring variety, once again I can write V of s as equal to the Laplace of the current, which is I0 divided by s, because it is a unit step, not unit step, a step of strength I0 divided by, multiplied by the impedance, which is equal to G divided by the admittance G plus J omega, no, SC, Laplace variable, not the sinusoidal, not a phasor, okay, G plus SC. And this I can write as I0 divided by S, and I can take C common, then I get S plus G by C, which I can write as 1 over CR. Have I done this correctly?
Yes.
Okay. So, in order to invert it, I write it like this: V of S is equal to I0 by C, then 1 over S times S plus 1 over CR, and the partial fraction expansion is extremely simple. I write simply as I0 by C. I can write this as S minus S plus 1 over CR, then I can have 1 and 1 by CR. Such things will come from experience. I do not have to do the formal partial fraction. Is it okay? S plus 1 by CR and CR cancel. So, and therefore V of t would be equal to I0 by C. 1 by S is U of t. U of t I will take out, minus 1 over CR e to the minus t divided by CR. Okay. Partial fraction is not correct. This is also 1. Here? How does this? Wait a second. S plus 1. I think this is correct. This is correct. All right. Do correct me if I make a mistake. So this will be I0 times R.
That C is also there. So I naught by C is there.
No. Oh yes. I naught by C is there, and therefore C and C cancels. I get simply I naught R. Let me write this correctly. I naught R. Now tell me if you have an objection. Is that okay? I hope so. All right. Now you see that it contains two terms. One is a constant and the other is an exponential term. And you can notice, you can see that that t equal to 0, the value is 0. Well, is it after you get a solution to a network by whatever means is possible? As I said, there is no replacement of common sense and
So 1 by CR, 1 by CR, 1 by CR.
1 by CR is not there. Okay. Anything else?
So in the second step, sir.
Second step here.
The second step, sir.
Third.
Should be 1 by CR. I naught by CR.
I naught by CR. No, I naught by C. I naught by C, and then CR I have taken out, and therefore C and C. Okay, you do correct that. Is this result okay? This result is okay. Which stage are you objecting to? This one? Third one. Okay, you correct that. Let me leave something for you too. Okay. Now you notice that at t equal to 0, now I want to bring physical concepts. As I said, there is no replacement for physical concepts. Okay, no mathematics, no amount of brainwashing can replace physical concept. Physical concept is that Vt is 0 at t equal to 0. Now, does this stand to logic? Look at this circuit. Vc 0 minus is 0, and Vc 0 minus is V of 0 minus. The capacitor cannot change its voltage instantaneously, and therefore V of 0 plus is also equal to 0. This stands to reason. Now, if this current stands for a long time, then the capacitor will be fully charged and will not allow a current to pass through it. So, the total current I0 shall pass through R, and therefore, at infinity V of infinity should be simply equal to I0 multiplied by R. Now, is this borne out by mathematics? Yes. This term goes to 0. as t tends to infinity, and therefore at t equal to infinity v of infinity would be simply equal to I 0 by r. So, the result is correct. All right. If I make a plot of v of t versus t, then the plot would be like this. It starts from 0 and goes to I 0 r at t tends to infinity. This is I 0 r. Now, this is my v of t in response to a unit step current. Suppose I want v delta t, then I can differentiate this. Okay? I can differentiate v u t and find v delta t, and you will notice that if I do this, well, I can write the expression v delta t. If you carry out this differentiation, as I said, you can either differentiate or go back to the Laplace domain if you so desire. All right. If you do that, then it is simply v delta t is I 0 by c, okay, multiplied by e to the minus t divided by r c times u of t. That is, it starts from I 0 by c and falls exponentially like this. Okay. This is the unit impulse response, you can do this by differentiation, or you can go back to the Laplace domain and carry out this thing. Okay. The third example that we take will illustrate the principle of superposition. That is, I consider the same current generator, let us say I of t, same current generator and the same resistance and capacitance, with V sub c 0 minus equal to 0, but I now consider I of t as a pulse rather than an impulse or a unit step. It is u of t minus u of t minus capital T, and as you know, the plot of this is like this. It is a pulse, it is a rectangular pulse of unit height and duration 0 to capital T. U of t is a unit step from which is subtracted another unit step at t equal to small t equal to cap T, and therefore this is the pulse. We want to find out the response to this. Now, obviously, because the excitation is a superposition of two unit steps, the response, I will call this I p of t, the response to a pulse. The response would be the superposition of two responses. That is, we will go back to the unit step response of this, which was equal to I 0 r 1 minus e to the minus t by c r multiplied by u t. This is the response to u of t. I am sorry, this is V p. Okay. This is the voltage response V. V p of t. This is the response to the first term, that is I u of t. All right. This is multiplied by I 0. Okay. The current is a pulse, a unit pulse multiplied by I 0. Yeah, amplitude would be I 0. Okay. Just to be general, it could be unity also, it does not matter. I 0 r multiplied by 1 minus e to the minus t by c r u t, and then the response to the second term, well, would be minus I 0 r 1 minus e to the minus, instead of small t, this is what time invariance brings in, that if you delay the input, the output is simply delayed by the same amount, nothing else changes. So, minus t minus cap t divided by c r multiplied by, instead of u t, it would be u of t minus capital T. Now, why is this? How come you multiply this by u of t minus capital T? That is because of causality. that is, the system is non-anticipatory. It cannot respond to u of t minus t before u of t minus t occurs in the scene. Alright. The previous response is due to u of t. So, linearity, superposition, time invariance and causality, all of them come into the picture, and this is why this example is a very interesting example. You cannot combine these two terms for small t between 0 and capital T. You cannot combine for small t between 0 and capital T, only the first term dominates. It is only at capital T that the second term shows its state, and the response can be, the total response can be drawn like this. As far as the first term is concerned, that is the response to u of t, well, it goes like this. The second term starts at t equal to small t equal to capital T, okay, and then it is negative, and therefore it goes like this. And if it was allowed to go to infinity, then it would have reached what level? This would have been minus I0 r, and this is plus I0 r. So, it is the combination of these two, it is the combination of this plus this. Between 0 and capital T, it is only this term that dominates. So, okay, and beyond this the negative, the cancellation starts its state, and therefore as t goes beyond capital T, it must come down like this. Ultimately at small t equal to infinity, the value would be 0, because this will be reaching I0 r, this will be reaching minus I0 r. So, this is the total response to a pulse. The excitation was like this. Excitation was I0, this was the excitation, and to the excitation, as long as the excitation is there, you notice this, that the voltage is rising, the voltage rises exponentially. As soon as the excitation is taken off, now comes the physical concept. What happens? Excitation taken off, the capacitor has charge to I0 r, not I0 r, less than this value, and then it discharges. The excitation is drawn away, so the capacitor charge gradually discharges, and this is why this exponential decay. Okay. Ultimately, when you allow sufficient time, the capacitor discharges completely and the voltage across it becomes 0. Alright. You must not divorce physical concept, because circuit theory is a mathematical subject. In fact, in no mathematical subject related to engineering, you should lose sight of what is happening physically. That is your best weapon. The best weapon of an engineer is physical insight.
So after the source has been removed, pulse is over, the source places a short circuit.
Open circuit, because that was the switch, and a current generator removed means it is replaced by an infinite. A voltage generator removed means it is removed by short circuit. Okay. Now, we have talked about step response, impulse response, we have also talked about sinusoidal response. Okay. What about complete response now? Complete response. As you know, the complete response of a network consists of two parts, the free response and the forced response, or what we call in terms of differential equation terminology, the complementary function and what is the other part? Particular integral. Okay. So, we will take two examples to illustrate how we derive complete response, and both of them would be interesting. Suppose I have an I0 sine of omega 0 t ut. Now, we are not finding the steady state response, we had found earlier, we want to find out the complete response now, and this is applied across a combination of a resistance and a capacitance with V sub c 0 minus equal to 0. We have already found out the steady state response for V of t, we have already found that out. the steady state response, we assess steady state of t. If you remember, it is I0 divided by square root of g squared plus omega squared c squared. This was done in the last class, in the third lecture, multiplied by sine of omega 0 t minus tan inverse, yes, omega 0 c divided by g. This is the steady state response or the forced response. To find out the complementary function, you have to write the differential equation and put the right hand side equal to 0. Obviously, the differential equation is GV plus C dV dt equal to 0, equal to the differential equation is I0 sine of omega 0 t ut, and to find out the complementary function or the free response, we have to put, let me use a color. If you want to find out the free response, let us call this as VF, then the right hand side is to be put equal to 0. The free response means the complementary function, okay. And you know the solution to such an equation, that is GV plus C dVF dt. You can write this as dV dt. Let us ignore the subscript f for a moment. dV dt plus G by C, which is 1 by CR V equal to 0. The solution to this equation is of the form V equal to K e to the minus T divided by CR, okay. The solution to this equation is of this form. Now the question is how to find out K. Let us put F again, the free response. How to find out K? You cannot find K by taking, this is a very important point, by taking this equation by itself and putting the initial condition. No. The initial condition has to be put on the complete response. You see, if you put initial condition equal to 0, obviously K would be equal to 0. Isn't that right? Whereas you know that when a transient, when a sinusoidal voltage source is applied across an RC circuit, there shall be a transient. Alright. So what you have to do is to find the complete solution first. The complete solution first. That is, the complete solution will be the sum of the two. So it would be K e to the minus T by RC plus I0 divided by square root of, I will not write the complete thing, sine of omega 0 t minus tan inverse of omega 0 c divided by g. You must remember this. To put initial conditions, to find the complete response, initial conditions have to be found on the total solution, not part of the solution, okay, not part of the solution. This is where you have to put the initial condition, that is, you put V0 equal to 0,
so
then find K.
So BF here is the free response.
It is the free response, yes. If there was no excitation, if I0, if there was no current source and the capacitor was charged at 0 minus, then this would have been the total solution. But the total solution here is that there is an excitation, and therefore you have to write the complete solution, then find the initial condition. If I do that, V0 equal to 0, then you get the following equation: K plus I0 divided by square root of G square plus omega square C squared, then sine of minus tan inverse omega 0 C divided by G, okay. Now if we want to find that, this would be equal to 0. Therefore K would be equal to I0 divided by square root of this sine of tan inverse omega naught C divided by G, and finding this is not a problem. This is omega C and this is G. If theta is the angle, then the perpendicular must be omega C and the base must be G, and therefore the hypotenuse is square root of G squared plus omega naught squared C squared, agreed, and therefore sine is perpendicular divided by hypotenuse, and therefore K would be equal to I0 divided by square root of this then omega c divided by square root of this, which means that it would be equal to I0 omega c divided by g squared plus omega naught squared c squared. Am I going too fast?
Yes, sir.
Yes, sir.
A bit?
Yes.
Okay. Tell me if there is a problem here. Is this okay? Finding the tangent? Well, the tangent is given. You have to find the sine. Alright. Now I combine, now I substitute back this in the complete solution, and the result becomes V of t is equal to I0 omega c divided by g squared plus omega naught squared c squared e to the minus t by CR plus I0 divided by square root of g squared plus omega naught squared c squared sine of omega naught t minus tan inverse omega naught c divided by g. This is the total solution. It can be written in a slightly nicer form, but before that, do you agree that this is the correct solution?
Yes, sir.
We have made a mistake. Don't trust me always. I sometimes intentionally make mistakes. That must be there. The whole thing has to be multiplied by ut. Now it can be written in a slightly nicer form like this: I0 u of t divided by square root of g squared plus omega naught squared c squared. If I take this common, then I get omega naught c divided by square root of g squared plus omega naught squared c squared e to the minus t divided by CR plus simply sine of omega naught t minus tan inverse omega naught c divided by g. So just a different form, and combine the terms together. All right. Then we take next example. So far we have dealt with only first order networks, that is one capacitance, one resistance, or in one of the lectures we took one inductance and one resistance. Let us see what happens when both the energy storage elements are taken into consideration. That is, we shall get then a second order equation. A second order equation is one in which the highest order of differential coefficient is 2. All right. This happens when an inductor and the capacitor both are present in a circuit. Inductor, the voltage is d I dt, whereas a capacitor voltage is integral I t dt, and therefore if I differentiate once more I shall get second differential coefficient of I t. And the example that we shall take is one which you shall come across again and again, that is, we consider a voltage source E of t u of t connected to a series combination of resistance, inductance and capacitance. And the problem is to find out the current I of t. You have done this exercise in W110. We will do it slightly differently. We will take Laplace transform and then try to solve it. Okay. In the process, we will bring certain terms into focus. We assume that I L of 0 minus equal to 0 and V sub C of 0 minus also equal to 0. All right. Then our differential equation becomes E t u t. Differential equation becomes E t u t R I plus L d I dt. You see, I L of 0 minus is of no concern, but 1 over C integral I tau d tau. Here, if V c 0 minus was not equal to 0, we should have written it, we would have to write it specifically 0 minus to t. And the simplest thing that one can do is to take the Laplace transform, that is, you get E of s equal to I of S multiplied by R plus SL plus 1 over SC. No, we are we are making E of S represent, we do not know what is E of t. There is, I think this requires a bit of consideration. You see, Laplace of U of t is equal to 1 over S. Laplace of a general function E of t, U of t, is not equal to E of S by S. No, it is not. There is a problem. If E of t is a constant, yes, capital E by S, but not otherwise. Okay. How do you find out the transform of this? Suppose you have x of t multiplied by u of t. You want to find the Laplace of this. Complex convolution. Complex convolution, that is, you do x of s star capital Y of s, all right, not the ordinary convolution, and there is a factor of 1 by 2 pi, all right. Okay, so please do not make this mistake. I have said E of S is the Laplace transform of E of t ut, okay, capital E of S. Now therefore capital I of S equals to E of S divided by R plus SL plus 1 over SC, and I can write this, let me write it again, I of S equal to, I can simplify this as SC E of S divided by, the denominator I want to write in the form of a polynomial, divided by S squared LC plus SCR plus 1. This I can write as S E of S. Now I want to write the denominator with the highest power term coefficient equal to unity. So I take LC out, then I get 1 by L S E of S, S squared plus S L by, no, R by L plus 1 over LC. That I can write as 1 over L S E of S divided by S minus P1 multiplied by S minus P2. It has two roots. This quadratic can be factored, will have two factors, and the factors are S minus P1, S minus P2, where P1 and P2 satisfy the quadratic equation S squared plus S R by L plus 1 over LC equal to 0. P1 and P2 are the roots of this equation, and as you know, P1 and P2 are called the poles of the function. Poles, the values of S at which the function blows out, it becomes infinite, are called the poles. The values of S at which the function vanishes are called the zeros. How many zeros does this function have? Depending on E of S. Suppose E of S is a constant, then how many zeros? No. If E of S is a constant, then how many zeros does this have?
Infinite and 0.
That is correct. Infinity is another point at which the function vanishes. So in general you must remember that all functions, no matter how it looks like, have the same number of poles and zeros. The number of poles is equal to the number of zeros. Here the poles are finite at P1 and P2. The zeros are, one of them is finite, S equal to 0, the other is at infinity. Okay? The number of poles must be equal to the number of zeros. Now the values of P1 and P2, P12 would be equal to minus R by 2L plus minus square root of R squared by 4L squared minus 1 over LC. Okay? That is very simple. It is a solution to the quadratic equation. These are the roots, and we shall denote this by minus alpha plus minus beta, all right. That is, this quantity we call beta and R by 2L we call alpha, all right. Then my solution for current is 1 by L S E of S divided by S minus P1 S minus P2. I have written this again, where P12 we have written as minus alpha plus minus beta. Alpha and beta have been properly defined. Alpha is R by 2L and beta is square root of R squared by 4L squared minus 1 by LC. Now, to be specific, let us now specialize the excitation. Let us say the excitation E of S simply arises due to a battery V, capital V. Then what is E of S? V by S, isn't it? E of t ut would be capital V multiplied by ut, and therefore E of S is equal to V by S.
So what is this V by T?
Pardon me?
So what is this V by T?
No, this is a battery. Plus minus. This is a battery. Okay. If E of t ut is this, then E of S is this, and therefore I of S, we are now considering a special case. I of S will be equal to V by L. S will cancel, and therefore we shall have simply S minus P1 S minus P2. Okay. We want to find the current, but before we find the current, once again we pause to look at the physical circuit. The circuit is this, and this is a battery switched on at t equal to 0. The initial conditions are the initial current in the inductor is 0, initial voltage across the capacitor is 0. So what would be I of 0 plus? It must be 0. What would be I of infinity if you look at the physical situation? 0. So it is only between 0 and infinity the current is allowed to play, whichever way it wants to go. It can go positive, it can go negative, and so on, alright. But 0 and infinity, the limits are constrained to be 0. The current must vanish. Okay. It is like a child which is born and the old man, he becomes an old man and then dies. Between birth and death, these two are constraints. Every individual must be born, must die. Here also the current is born at t equal to 0, and then it must die at t equal to infinity. Let us see what happens in between, and this in between story depends on the value of beta. You recall beta is equal to square root of R squared by 4L squared minus 1 by LC. Therefore, depending on the relative values of R, L and C, beta can be real, can be equal to 0, or can be purely imaginary. We shall consider all the three cases separately. First, let us say that R squared, case 1, R squared by 4L squared is greater than 1 by LC, which means that R squared is greater than 4L by C. Alright, that is beta is real and greater than 0. Of course, you are taking plus minus beta, isn't it? So, P1 therefore is equal to minus alpha plus beta, and P2 is equal to minus alpha minus beta. And our equation I of S is given by 1 over L. Now it would be V by L, alright. Then A by, now we make partial fraction expansion, S minus P1 plus B by S minus P2. And you can easily see that capital A would be P1 minus P2.
Capital A would be P1 and B can be minus P2.
No. What is capital A?
Yes.
Capital A is 1 over P1 minus P2, and this would be equal to minus B. Agree? That is very simple to see. How do you find capital A? You multiply this by S minus P1 and put S equal to P1. That is how you get 1 by P1 minus P2. Alright, and B would be exactly the negative of that. But what is P1 minus P2? if you look at the values of P1 and P2, it is simply equal to twice beta. Agree? P1 minus P2 is twice beta, and therefore, if I omit a couple of steps, I can write I of S. No, just one step I omit. V by twice beta L, I take A and B out, multiplied by 1 by S minus P1 minus 1 over S minus P2. And therefore, I of t, if I take the Laplace inverse, it would be V by twice beta L e to the minus P1 t e to the plus P1 t, yes, which would be e to the minus alpha t e to the beta t minus, agreed, this is minus alpha plus beta, okay, minus e to the again minus alpha t, but e to the minus beta t, okay, multiplied by ut, quite correct, which I can write as V by 2 beta L e to the minus e to the beta t minus e to the minus beta t. No, I have missed a term, u of t, I have missed the term e to the minus alpha t. Now, this obviously physical concepts, physical considerations, let us check against this mathematics. At t equal to 0, this is indeed 0. At t equal to infinity, this is 0. Now, this term e to the minus alpha plus beta times t depends whether beta is greater than alpha or alpha is greater than beta. Here, beta is greater than or less than alpha? Less than alpha, because alpha is r by 2l and beta is r squared by 4l squared minus something square root of that. So, this also will go to 0, and therefore, I of 0 equal to 0, I of infinity is also equal to 0, which is correct. And in between, can it go negative? Well, if you recall the definition of hyperbolic functions, this is simply twice shin of beta t, and shin can never be negative, all right, shin can never, and therefore this whole quantity is positive. In other words, the variation of I of t versus t shall be of this form. It will rise from 0, it will get a maximum and then fall to 0. Okay, is that okay? This is how the current varies. Now, we consider the next situation, that is case 2, in which beta is equal to 0, which means that r squared equal to 4l by c. If beta equal to 0, then you see P1 and P2 are both equal to minus alpha, and therefore, the solution, this is a case of repeated roots. The solution for current I of t will now be of the form k1 plus k2t multiplied by e to the minus alpha t. Is it agreed? ut, okay, ut. Now, the problem is to find k1 and k2. Where are the initial conditions? How did we get this thing? Well, it is a differential equation, or you take the original I of s. Just a minute. I of s, let me check the expression, is equal to V by L 1 by S minus P whole squared, where P equal to minus alpha. I take the inverse of this. Well, I can get k1 and k2 directly from here, right? Can you tell me what is the inverse of this? V by L e to the power pt what S s square T. Agreed? Now I wanted to go from the differential equation. Suppose I do go from, I don't take the inverse of this, I go from the differential equation or from previous knowledge. Since the roots are repeated, my solution would be of this form. Okay. Now how do you find the initial conditions here? Well, one initial condition we know, I of 0, that is 0, and therefore K1 should be equal to 0. There is no other way. How do you find K2? T equal to infinity, it is again 0, but that does not give K2. Derivative. Alright, you must be aware of this. The shortcut is you take a Laplace transform table and invert it. Suppose that table is not available and you have forgotten what the inversion is. Then you go back to the roots. How do you find out K2? Well, if you write the equation, if you write the equation V u t, the original differential equation, what is it? Ri plus L di dt plus 1 over c integral 0 minus to t I tau d tau, and put here t equal to 0 plus, then the left hand side becomes V equals to I 0 plus is equal to 0, therefore L I prime 0 plus, and what is this quantity then? 0, and therefore I prime 0 plus is equal to V by L. Is the point clear? To find K2 we have to take the first differential coefficient value at t equal to 0 plus, and this is how we find I prime 0 plus, and if you substitute this in this, take I prime, take the differential coefficient, put t equal to 0 and put that value equal to V by L, you shall get exactly this solution. Okay. So there are different ways of arriving at the same solution. Nothing succeeds like success. The final result must be correct. Okay. If you have made a mistake in between, fortunately for engineering, as I said, physical concepts, there is no substitute. For engineering, there are at every step you can check whether it stands to reason from physical consideration. The result that you have got, does it stand to reason from physical consideration? Okay. Now we go back to the plot. You see, my solution is that where is the solution? Okay, this is the solution. This is the solution. All right. Now obviously at t equal to 0, well, what is p? P is minus alpha. At t equal to 0, this is 0. At t equal to infinity, does it become 0? T times e to the minus alpha t. The exponential decay is faster than linear rise. You know that. If you don't, you can expand t by e to the alpha t. Expand this, divide by t, then you will see that it becomes 1 over sums of powers of t. At t equal to infinity, obviously that goes to 0. So our physical conditions are satisfied, that is, it starts from 0, it dies at infinity. In between, can it be negative? No, it has to be positive. Now therefore the curve, the plot shall be similar to this, it shall be quite similar to this. Would it be above or below this? That is the maximum. You see, this case is for r squared greater than 4L by C. Would the maximum value be greater? Physical concept, you can verify later, you can find out what this maximum is, what the other maximum is by differentiating, putting it to 0 and so on, but physically it should be greater. Ultimately, of course, it dies down to 0. So this is the case for r squared equal to 4L by C, and this case is called the case of critical damping. critical damping. This is the critical value of resistance below which the response would be damped. This case is called over damped response. That is, over, the adjective over stands for more than critical. That is, the resistance in this circuit is more than the critical value. And as we shall see in the next lecture, if it so happens that R squared is less than 4 L by C, well, the response is still of general shape, but it will rise further, but it crosses 0 earlier than infinity, can become negative, and then goes on oscillating in a damped manner. The decay of the peaks is exponential, and the rule is e to the minus alpha t.
So does all the peaks appear at the same point?
Do all the peaks appear? That I leave it to you to find out. I might ask you this question in one of the minors. Okay, things I leave to you remain in my mind while setting exam papers, and therefore take them seriously. All right.
What was the question?
The question was, do all the peaks occur at the same point? Well, all the peaks, the magnitude is different, that is obvious. Do they occur at the same point? I won't answer, I leave the answer to you, find out. You find out, okay. But the interesting point is that the value of R causes the circuit response, changes the circuit response tremendously. You see, as long as capital R satisfies this relation, R squared equal to or greater than this, the current can never go negative. It shows a maximum, then comes down. But when as soon as R satisfies, the R goes below this value, that is R squared is less than 4 L by C, the current behaves like a delinquent child. It goes on oscillating between positive and negative till it is forced by this damping factor e to the minus alpha t to ultimately come to 0 at t equal to infinity. That must be satisfied. Birth and death, these are constraints. In between, it can either remain positive or it can oscillate. The third case is the most interesting case, and we shall consider this in the next lecture. Thank you.